All right, we're in section 10.2, which is our last section that we cover. So this will be one of our last videos. All right. Well, the 10.2 is permutations and combinations. We did 10.1, which was counting, and we're still counting, but we're counting with more tools. All right, now, this wasn't in Chapter 10, but in Chapter 9, we studied combinations. We might not have called it that, but we did the binomial theorem when we did this NCR. And do you remember the formula for NCR? It was the top factorial divided by the bottom factorial divided by the difference factorial. So that was the formula for NCR. Well, we're going to talk about another formula along with NCR, which is NPR. Now these are usually, neighbors on your calculator. If you can calculate NCR, you can calculate NPR with a calculator. This is the way it is on a calculator button. Our book writes it with a P parenthesis NR. And so there really isn't a top and a bottom this time. There's a first and a second. So what's the formula for permutation? If for combination it's top, bottom, difference factorial. Well, I'm going to say first, because there is no top. First factorial divided by the difference factorial. And that's it. So it's a shorter calculation. By the way, you'll almost never use these, calculators have replaced the need to do these, certainly. But you'll never use this one for several reasons. But let me go ahead and do one. Let's do 26P4. So this is a calculation. This is saying calculate 26P4, or that's the way a calculator would write it. The way the book might write it is P parentheses 26, comma 4. And we haven't talked about what it means yet, which I'll get to soon. But I know it's 26 factorial divided by the difference factorial, which is 22. Now these are huge numbers, so big they would require scientific notation to calculate, to show on your calculator. But I know I can take 26 factorial and write it as 26 times 25 times 24 times 23 times 22 factorial, because that would just continue to 1 over 22 factorial. So what is 26P4 really? It's really 26, 25, 24, 23. So this whole formula is probably not something I really needed. A better way to describe it is it's the first 1, 2, 3, 4 terms of 26 factorial. So we actually see the numbers in here. It's a little hard to say with N and R. I guess we could say it's the first R terms of N factorial, but it's the first 4 terms of 26 factorial. If I multiply those out, I get this calculation. Now that's different than 26C4. That is calculated a different way. And we'll get a chance to see it, but I just want you to know they're different calculations. All right, so we're talking about solving counting problems using permutations, using combinations, and then they distinguish some other things, non-distinct objects versus repeated objects. We'll cover all of these, but we're counting. A permutation is an ordered arrangement of R objects chosen from N objects. So I like to use this three-word phrase, select and arrange. With combinations, you're just selecting. With a permutation, you're selecting and arranging. And that's going to be a big issue, the difference between when to use permutation and when to use combination. All right, well, let's get to problem. All right, a company assigns 4-letter codes to represent clients. When they say 4 letters, we're assuming that it doesn't have to make a word, so there doesn't have to be vowels. But that's exactly what you want to do when you see something like this, is actually try to put yourself into the problem. If repetition is allowed, so repetition is allowed, that's very important. In forming this code, how many 4-letter codes are possible? Well, the technique for doing something like this is to get yourself into the problem, and I like to pick a code. So let's say I picked A, Q, Z, D. Nothing special about that choice, but what choices did I have? In other words, how many choices did I have when I laid that A down there? Well, I had 26. And how many choices did I have for the second line? Well, once again, 26. Remember, it said repetition is allowed, so it's not like once I pick A, I can't use it anymore. I picked that one. I picked this one. So it turns out it was 26 to the 4th power. And sometimes we like to leave our answers like that. In fact, this case I will. I could multiply it out, but whatever 26 to the 4th power is would just be a big number. And it would take me kind of away from understanding this question. So 26 to the 4th is a good way to answer that question. Notice we used the multiplication principle we talked about in the last section. How many ways to do the first task, second task, third task, fourth task, and it gives us the result. They actually did calculate it. But so it's a lot of potential clients. If we're giving every client a different code, we can go almost 500,000 clients this way. Well, they put this in a specific format. If you have distinct objects with repetition, you're not using the permutations formula, the NPR formula on your calculator. It's just N to the R. So if you were to select, what was it, from 26 objects, select and arrange 4 objects chosen from 26 objects, the order is important here, it would be 26 raised to the 4th power. That's what they're just telling you what we did earlier. Again, it's better to get into the problem, make yourself an example, and actually pick the numbers, and then calculate the 26 to the 4th. But they're just making it official with that formula there. So this is another example. This time they're saying without repetition. So 1, 2, 3, 4. Let's pick. If I said A, well, I can't do that. Remember, I can't repeat. So I can pick another number, another letter. Let's say I pick D. And then let's say I pick Z, and let's say I pick, well, I can't pick D again, so I have to be selective here. What can I pick? Well, I can pick anything as long as it's not A, D, or Z. So I'll pick B. All right. Now, this is just my example or my sample that I put down there. But I really could have picked A through Z on this first choice. So I certainly had 26 choices. Now there was one letter I couldn't pick when I got here because it's without repetition. And so the one letter I couldn't pick is whatever letter I picked over here. So without being able to pick A, I had 25 choices. Without being able to pick A and D, I had 24 choices, and then finally 23 choices. So whatever 26 times 25 times 24 times 23 is, that's the number of choices I had for this particular problem where you're taking you're making 4-digit codes with 20s using any 4 of the 26 letters of the alphabet. Now, what is this? Well, this is 26P4. It's really awkward for me to write it this way, but that's the way the author wrote it. It's better to write it this way, 26P4. This is the way your calculator does it, this is the way the website does it. Now, sometimes they will actually, it'll be a multiple choice question or some kind of question where they'll say, which calculation will calculate the answer to this? And you actually need to know it's 26P4. We didn't need to know that because if all we want to do is get the number, we just multiply these together. But I do need you to be able to be aware of this formula. If you have the first 4 characters of 26 factorial, it's 26P4. All right, so they go through the calculation. Some possible calculations, they do a bunch of them. And they go ahead and use the multiplication principle, just like we did. Calculate it. And then they make it official. The notation PNR, or NPR with subscripts for the N and the R, represents the number of ordered arrangements of R objects chosen from N distinct objects, where repetition is not allowed. So this is what I was saying. We're selecting and arranging. So if you imagine you have the entire alphabet laid out as on cards or something, and I wanted to select 4 of these, but I wanted to select and arrange 4. So I wanted to select 4 of these, but the arrangement made a difference. In other words, A, B, C, D is not the same as D, C, B, A. Those are 2 different clients, 2 different words. So if I'm selecting and arranging them, that's what NPR calculates. And it is the same calculation as we calculated with the multiplication principle, but it's just using this rule or this principle. All right. And how many ways can 6 people be lined up? The 6 people are distinct. Once a person is lined, that person cannot be repeated elsewhere. Well, there's 6 places to put the first person, second, third, fourth, fifth, and the 6th person. So the idea is we could start this problem with a multiplication principle, or we could use our new rule. There are 6 people, and we just want to arrange them. So we want to take all 6 and arrange them. So notice they had 6 people, and we wanted to line up all 6 of them. So of the 6 people, we select and arrange 6 of them. It would give you the same result for that count. So now they're giving you the formula in its more official version. So this is what I meant by first factorial over the difference factorial. You know, this is so much easier than this formula. I said you're not going to use this formula. I guess you could, but, you know, the secret's already out. 6P2 is the first 2 characters because of that 2, of 6 factorial. Remember, factorial would be 6, 5, 4, 3, 2, 1. So 6p6 was the first 6 characters of 6 factorial, meaning all of them. The first 2, well, we know that's 30. The first 1 term of p factorial would just be 5. The first 4 terms of 62 factorial, 62 times 61 times 60 times 59. So these calculations, when I introduced this to you, I said you'll probably never use it, but they're using it now. At least on a few of these examples, they're using it. A lot of work to go through for something I knew was just going to be the 1 term of 5 factorial, which it kind of did. But yeah, they ran it out here. Or you could use a calculator. And a calculator would give you the result of all those multiplications just by you knowing how your calculator calculates this. What are they asking here? Okay. What is the problem? The birthday problem. All we know about Carl and Bob is that they have different birthdays. If all the possible ways this could occur were listed, how many would there be? Assume there are 365 days in a year. So they're saying, how many possible birthdays, combinations is there? Well, I should say, how many ways could that happen? All right. So they're saying that what we're going to do is going to select 2 birthdays and arrange them or assign them. So there are 365 days, and we have to select 2 different ones. Hopefully you see what I'm saying, right? There are 2 people with different birthdays. So that means, let's get into the problem. Let's say Carl has a birthday on 5/4, and Bob has a birthday on not 5/4, so any other day. Let's say he was born on Christmas Day, 12/25. So 2 choices. Well, how many choices did I have? I had 365 choices for Carl. And then I had 364 choices for Bob. So the calculation boiled down to multiplying these together. And again, I could have gotten that directly from the multiplication principle and just started here and gone here. But the book is saying what else you can do is think of it as 365 to choose from, and we're going to select and arrange 2 of them. When I say select and arrange, it's different if, certainly different to Bob and Carl if I switch their birthdays. So we have essentially 2 ways, start it here or start it here, to get this calculation. There are this many ways for 2 people to have different birthdays. Now, we've already talked about combinations, but combinations, our use for it was different. In this case, combinations is going to be we select, but we don't arrange them. So I don't like the word arrangement. Kind of gives you the wrong impression of this calculation. But NCR, it's the same NCR we saw in another section written this way and this way. All right. It represents the number of combinations. Okay, yeah, that's right. Of n objects taken R at a time. but we're not regarding the order. So, example 6, list all combinations of 5 objects from taken 3 at a time. So 5 objects are A, B, C, D, E, and we want to take them 3 at a time. Well, they just want us to list them, but how many is it? Well, I'll trust them down here. I wouldn't trust myself to do this unless I had some time and a little preparation, but there's ABC. So just taking the first 3, there's ABD, ABE, but you can see how it all works out. And assuming they listed all of them, there are 10. But how do we know there are 10? Well, we know from the recent rule here that the way we count the number of, we'll call them subsets of size 3 from a larger set of size 5 is 5C3. And to calculate that, it's 5 factorial over 3 factorial divided by 2 factorial, which we actually have seen this earlier, it's 10. Now I say that we're not looking at order, and what I mean by that, and I say these are subsets, notice they didn't list CBA as a separate entry here. We're not doing combinations, or sorry, we're not doing permutations where we select 3 and arrange it. ABC is not, we don't want to count all the separate arrangements, or correct word, permutations of ABC. We want to count ACB, BAC, all of these others. So since that's true, we use NCR to do this calculation. When you're just calculating without regard to order, it's NCR, the C. If it was regard to order, if somehow they're going to say, all right, you have A, B, C, D, E to choose from, and you're going to make, how many words of length 3, we'd use P for something like that. I'll use another example for the distinction. But the book seems to have forgotten that we just did this in the previous chapter, and we didn't use this notation, we used this notation. But we're using it again here. So we used it with Pascal's triangle and binomial theorem, but we're using it again. All right, so now let's do some calculations. This is interesting. MC0, it's 1. But how do we know that? Well, we run it through the formula. And remember, 0 factorial is 1. So 0 factorial is 1. So it all calculates to be 1. Be able to use your calculator. That pays off. All right. So we have some actual word problems here. So when we have in a word problem, the word committee, we're assuming that order doesn't matter. It doesn't matter how the committee is chosen. It doesn't matter if you're chosen first or last. It's a committee. It's not like the alternate problem where they have a president and a vice president. If you switch the president and the vice president, that's a different administration. But if you're just putting together a committee, think of committee as a combination problem. All right, we have 5 people from a pool of 8 people. So there are 8, applicants, and we're going to pick 5. How many is that? Well, it's 8C5. You run that calculation and you get 56. There are 56 ways to form this committee. This would be a very hard question to answer without this science, right? Without being told that there's this button on your calculator that does exactly this. And it's the NCR button on your calculator that does exactly this. It tells you the number of subsets of size 5 from a larger set of size 8. That's what it does. Use that button on your calculator or set it up to calculate it yourself, and you'll find the number of committees. All right, now what's going on here? It looks like we're going to have multiple tasks. And how many ways can a committee consisting of 3 faculty members and 4 students be formed if 7 faculty members are eligible and 9 students are eligible? So from the 7, we're going to choose 3, and from the 9, we're going to choose 4, and we're going to multiply those together because we consider it task 1 followed by task 2. So that's exactly what they did. Multiply those together, calculate each one separately, and multiply them together, and you get this number. So multiplication principle where they multiplied the 2 separate calculations. All right, you have some of these type of questions. How many different words, real or imaginary, can be formed from the letters of the word arrangement? So, yeah, I usually like doing something like this, but we're going to need some help on this one. I know there are 11 choices I can put here. I can pick this A, this R, this R, this A, this N, the G only occurs once. I can pick either of those E's, the M. All right, but there's 11 choices for that. And there's 10, there's 9, there's 8, 7. Those are the number of choices I have for each of the 11 words. So if all of these words, all these letters were different, if it was just the first 11 letters of the alphabet, this would be 11 factorial. But notice that some of the letters are repeated. So let's say I actually, this were one of my arrangements of the letters of the word arrangement, A-R-R-A-N-G-E-M-E-N-T. But let's say I switched the 2 A's, because I counted that. In this 11 factorial, I counted this A as essentially different than this A. But they're not. So I have to do something about the repeated letters. So they talk about that here. There are 2 A's. The A's are repeated, the R's are repeated, the N's, the E's. Nothing else is repeated, but 1, 2, 3, 4 things are written twice. So 11 factorial answers a different question. 11 factorial answers the question, if there were all different, it would be 11 factorial. Let's get to the formula here. Okay, here it is. Here's essentially our formula. They spent a lot of time getting there. And I'm going to get rid of these ones here. All right. It's 11 factorial. We knew it was going to be 11 factorial somehow in this discussion, but I want to divide by 2 factorial because there were 2 A's, 2 E's, 2 R's, and 2 of another letter, whatever they were. But I want to divide by each of those factorials. So let's go back to the question where we can see it. 11 factorial if there was no repeats. But the A's are repeated, and there are 2 of them. If there were 5 of them, I would write divide by 5 factorial. But I'm just going to divide by 2 factorial because of the repeated A's. I'm going to divide by 2 factorial again because of the repeated R's. The repeated E's and the repeated N's. I don't have to divide by anything because t, well, t is not repeated. Remember, this 11 factorial is assuming things aren't repeated. It's the times when they are repeated that I need to do this division. So the calculation is just 11 factorial. Okay, that's big enough that I'd let the calculator do it. But divided by 2 factorial. Now 2 factorial is just 2 times 1. So that's 2 times 2 times 2 times 2. That would be 16. 11 factorial divided by 16. If you ran that through a calculator, you would get this number. So almost 2.5 million arrangements of that letter. And they give you this formula. So if you're arranging something, the entire thing, you're arranging something where like all of the letters in arrangement, n factorial divided by each of the repeated values factorial. Arranging flags. How many different vertical arrangements are there of 9 flags if 4 are white, 3 are blue, and 2 are red? So we have 9 objects that we're going to arrange. So 9 objects arranged can be arranged 9, 8, 7, 5, 4, 3, 2, 1, 9 factorial ways. But the repeated values have to be divided or belong in the denominator. So 4 factorial, 3 factorial, 2 factorial. So make sure you can calculate something like that, but calculate this and you get this number of arrangements. That's the flags problem. All right, I know there's a problem on your homework that's not here, so let me talk about that real quickly. And that is more about forming a committee. So this question, example 8, had said, how many ways can you form a committee with 5 people from 8? Now, what if the question had said, how many ways can we get a president, a vice president, a secretary, a treasurer, and what's another office, and a CEO, all right, from 8 people. So this is very different because, well, it's not all that different. It's just a button that we push that's different. But it's different because it would be a different, a list of officers if the president and the vice president were interchanged. So when they say committee, use C. But when they say president or any other specified office, use P. I want to not just select 5 people, but I want to arrange them. So it's going to be P8-5 instead of C8-5. That's going to be a much bigger number than 56. It's going to be 8, 7, 6, 5, 4. Is that right? 1, 2, 3, 4, 5. Yeah. The first 5 numbers of 8 factorial. And I'll go ahead and do that calculation. So here's my calculator. I assume I have on this calculator, even though it's not the greatest calculator, but the light's not that great, the NPR button, but I don't need it. I can just do 8 times 7 times 6 times 5 times 4. If I didn't miss anything, it is 6,720. So remember, there's only 56 ways to make a cabinet and 6,000 ways. That's really a big difference. But I'm going to stay with that. I don't think that's off. Let's see. Yeah, that's the way. Or maybe one of these is off. I'm not sure. Nope. I think that's it. So permutations are much, much bigger. There's a lot of a big difference when you change the order. And that's just what I wanted to point out. So use permutations when they say president. I guess that's a quick way to do it. And use combinations when they say committee. All right, well, this turned out to be a very long video for one particular section, but it was one take on one section that a lot of students haven't studied. So if you've taken many, many algebra classes, you probably still didn't talk about permutations or combinations, but I think it's a good lesson to leave us with, something new, and since it is part of mathematics and other branches of mathematics, certainly worth looking at. All right, so that's what's probably going to be our last video for this section for the course. So enjoyed having you all in the class, and I will not see you in another video, but I'll see you on the My Math